You okay right there?
Yes, sir.
Okay. All right, well, 9 a.m., shall we? First things first. So I realized, it was brought to my attention, I had forgotten that we have a test scheduled for Tuesday, right? Today. Next class, we're supposed to have a test. So it kind of crept up on me because you can see normally we need to cover through 2.6 before we get to this test. So I kind of lost track of time here because we're a little bit behind right now. So I was going to propose that we move that test. I don't want to ruin anyone's schedules, but I really think we would be better suited to either have this test on the 7th of March or the 9th of March. So if we do the 7th of March, you at least have a weekend before. If we do the 9th of March, that's the last class before spring break. So what do y'all think? 7th? Let's take a vote. 7th? Okay, let's do that then. Now, I can't tell you exactly what will be on the test because we need to see how we do with 2.5 and 2.6. All right? So officially, exam 2 is now going to be March 7th. All right? Okay, that's the first order of business. The next thing, any questions over homework or anything from product and quotient rule? I woke up, my throat hurts today, so I hope I don't get people sick. I'm kind of in the splash zone here. No questions? Product quotient, we're all rock solid on that? Feel good? Yes? Okay, so I said last time that today would be an important day, right? Because we're going to cover what today? Chain rule. All right, so let's get to it. All right, so I thought this is the way I would kind of get things motivated. What I'm going to do here is I'm going to graph a function for you. The test is moved. Okay. I'm going to graph a function here for us. Let's do f of x equals sine of 2x. So we're looking at the function here. F of x is sine of 2x. And I'm going to zoom in on it a little bit for us. I'm also going to change the x-axis so that instead of giving us like 0, 2, 4, 6, it'll give us things with pi in it. So to do that, I just come over here and I just do pi. I just type pi. I'm going to do pi over 6 like that. Okay. So right here, this is the graph of sine of 2x. And let's do something that we did a few classes ago. Let's see if we can sketch the derivative of this function. All right? Because that's something you'll have to do on that test. So if I go to graph this derivative, the derivative of this function, what I would do probably to start is look at all the places where I know what the derivative is. And when I say derivative, I mean I know the slopes of the tangent lines at those points right there are what? What's the slope of tangent lines here? What is it? 0, right? So when I graph the derivative, that derivative should have points. At the same x value, I should have a y value of 0 on that derivative. So 0 here, 0 here, 0 here, 0 here, 0 here. Right? Okay, how about between here and here, would my derivative be positive or negative if I'm in this region? Positive. So it's got to be positive, starts here at 0, the derivative starts at 0, and then it's positive and then goes back to 0, right? So when I go from here to here, I got to go up and then back down. So I'm going to draw that. Looks something like this. And then when I draw this from here to here, right? The graph's going down, so my derivative should be negative. I'm just kind of guessing here. And then it goes positive again, and then negative, and then positive and negative. That's my rough sketch. What's up with all the chairs? I don't know what's going on here. We have less chairs, or less seats. Do you want to sit right here? Okay. Are you okay over there? Okay. Okay, so that is the picture. I think that's a rough picture of what the derivative is, right? I'm just kind of, I know for sure that these points are on my derivative. I'm sure that this is positive and then negative, positive, negative, but I don't really know how high it goes and how low, but that's my rough guess. Now, let's go back to the algebraic function. And let's talk about how would we take the derivative of this, all right? So we've learned how to take the derivative of, why is everybody here today? Yeah, we can, well, it's just not a very, can we let's do this. Let's turn this table 90 degrees so that you get people on this side, yeah. No. You're gonna be more sideways now, but you come on this side. Do we have enough chairs or no? Yeah? Okay. Y'all figure out. Turn a little more. That'll work. Will that work for you all? Yeah. We're happy? Okay. All right, so we know how to take the derivative of x to a power, right? We can do x to a power. We know how to do that. We know that if we have a function, right, times another function, we have the product rule from last class. We know that if we have a function divided by a function, we have the quotient rule from last class. So we can handle all of this, right? So when I look at this, That's obviously not x to a power, right? Is this a product? I'm seeing no's. Why is this not a product?
That's the argument.
It's the argument. Okay, so when we say this, we would say sine of 2x, right? We don't say sine times 2x. So one of the key things today is for you to understand the difference between multiplication and functional composition when a function is being plugged into another function. So here we look at this as being the function 2x being plugged into the function's sine, right? So imagine like a chain of events here. If you were to take x and plug it in here, the first thing that would happen is you would go 2x, right? And it would come out. And then you take that answer and you plug that into the sine function, and that would come out as sine of that 2x. That's called composition. Back in college algebra, you might remember the Fogg and Goff thing, f of g of x, g of f of x. That sound familiar? That's the idea here. We have composition of functions as opposed to multiplication. So what would your guess be? Does anyone have a guess? Not if you've seen this before, that's not a guess. So does anyone have a guess as to what the derivative of this might be? Well, we have a sine function, right? So probably cosine, right? So cosine 2x? Yeah, is that what you're saying? Yeah? Does that seem reasonable to everybody? I mean, we know the derivative of sine of x, right? What's the derivative of sine of x? Cosine x, right? Here we have sine of 2x, so it seems reasonable to think that the derivative would be this. The question is it, right? Is that the answer? Well, let me graph cosine of 2x, and let's take a look. So I'm going to graph cosine 2x. Wow. Seems like we have the right answer here, right? Okay. But we don't. And here's why. Here's why this is not right. Let me take it off of there. Let me hide this for a second. I want us to look at this. I'm going to zoom in on this right here. Okay. Right here at this point, the slope of the tangent line there is positive, isn't it? And would you all agree that it looks like it's approximately, I don't know, something like that? Yes? Can you all tell, if I were to extend this line, let me extend this line. Actually, let me cheat a little bit. I'll do it this way. There. Do you all agree that that's a tangent line? That looks like the tangent line there? Can you all tell by looking at that line what its slope is?
More than one.
More than one. How do we find the slope of a line? Rise over run? So if I go from this point, let's see, to maybe get to that point right there, I would go at what? Up 2 and over 1. That has a slope of 2, doesn't it? Let me bring the derivative back here again. I'm going to graph the cosine 2x. I said derivative. We think this might be the derivative. But do you see that? What's the value of it here? It's 1. It needs to be what? 2. It needs to be up here, doesn't it? Right? To match with this slope, I need that to be up there at 2, and it's not. So I need to kind of like stretch it out, right? Do y'all understand what I'm saying? I could do that for all these points, like right here. There. See at this one right here, take that derivative out of there again. Okay, at this, gosh. There. At that point right there, right? I'm not exactly there, but what would you say approximately the slope of that line is? 2, but which way? Negative. So it's negative 2. It's like this slope was 2, right? Over here, it looks like it's negative 2. And then here it'd be 2 again, right? And then over here, it's negative 2. So it's like what we thought it was, right? This cosine 2x. The problem is it's not going high enough. These aren't going high enough. This isn't going low enough. This isn't going high enough and then low enough. Got it? So this is not correct. We're missing something here. We're missing something. So what do you think we're missing? A 2. We're missing a 2. See, because if I take this and I multiply it by 2, what does it do to the cosine function? Think of that 2 as like being in the front here. That's like an amplitude, right? And that would stretch it out. So it seems like maybe the derivative of this, or the derivative of this, should have been what we thought it was first, right? The cosine of 2x. But then I needed to multiply that by 2. All right? And that is the correct derivative. But let's see if we can understand how we're going to get that answer. Like, I'm trying to get you to see how the chain rule is going to eventually work. All right? So what does it look like I did? First, I took the derivative of sine of 2x and just said, oh, okay, that should be just cosine of 2x, right? But then after I did that, I multiplied it by what? 2, but where's that 2 coming from? It's the derivative of what? The 2x, right? What's the derivative of 2x? It's the 2. So it's kind of like an onion. It has these layers. The outer layer, if you look at this function, the outer layer is the outer function is sine. The inner layer is the 2x. Understand that idea? So taking the derivative, I start with the outer layer. What's the derivative of sine of anything? Cosine of that, whatever, anything. So here it is, cosine of that, anything. Then I say times, now I forget the outer layer of the onion and I go to the inner layer and I take the derivative of 2x, which is 2, and I tack it on. That is the way the chain rule works. I'll put it up formally here in a second. I'll give you the actual rule. But let's see if we can't do another one without the rule like written on the board. Let's say I gave you f of x is, let's go with sine again, sine of x squared plus x. And I ask you for the derivative. All right, you look at this and you say, okay, I have composition. I have sine of x squared plus x, right? Outer layer, inner layer. The outer layer of this function is the sine function. The inner layer is the x squared plus x, right? So we start with the outer layer. What's the derivative of sine of x squared plus x? Cosine of what? X squared plus x. Do not go taking the derivative of this yet. Okay? Because we're working on the outer layer first. So you'll see me do this. I like to grab random objects and do this. This is a mouse pad, okay? So if I put a mouse pad right here, what is the derivative of sine of a mouse pad? Cosine of the mouse pad, right? Do you see that that's exactly what we have there? So derivative of sine of a mouse pad is cosine of the mouse pad. And now what I do is I say, okay, I've already taken care of that. Now I can remove the mouse pad and look at that and now take the derivative of that. And derivative of that is what? 2x plus 1. You can do that term by term, right? Because there's a plus between them. So you just do power rule on this. 2x plus derivative, that's 1. And I need to put it here. With a multiplication, I need to put that answer right here. 2x plus 1. So is that correct? Do you think that's right? I'm telling you that that's what you're supposed to do, but is what I wrote on the board correct, do you think? I need parentheses. I must have parentheses around this. I have to. And it's not optional. You get points taken off if you forget, and here's the reason why. What we're doing is we're taking this and we want to multiply it times that whole thing, right? So it's like if I write this down, 4 times 3 plus 2, what's that answer? 14, right? You do 4 times 3 and then you add 2. But if I do this, that's a different answer, isn't it? Because now you do this first, then times 4, and that's going to be, what, 20? So what are we trying to do here? This is kind of like 4 times not 3 plus 2. We want this together, okay? So I must put this in parentheses. Now, if this was only one term, like in the previous example, it was only a 2 that came out, right? I didn't need that 2 in parentheses, so I just left it.
Could you still put the 2 in parentheses?
You could put it in parentheses. It would just be kind of parenthesis abuse, but it wouldn't be wrong. One of the things that students do, I'm not saying this is you, students that aren't comfortable with parentheses, they just start throwing parentheses on everything just to try and be safe, but that can actually be incorrect too, because you can actually put too many parentheses and it be something other than what you are trying to make it be, right? All right, let me do another one, okay? Let me do another one. Again, I haven't formally given you the rule, because the rule I give you, even after I give you the rule, it's not going to help you the way this one did. These were like it was a formula, right? Derivative top, right? Derivative first one times second plus derivative that one times. That was a very formal rule. The chain rule is more of a conceptual rule. So try this. What if we have f of x equals, let's switch it up. Let's go to tangent, and I'm only using trig functions because they're the easiest to see the composition happening. Tangent of, sine x. That is not multiplication, right? This is not, that over there is not this. I did not give you this function. Right? If I write this, that's a product, isn't it? This is tangent x times sine x, and if I wanted you to differentiate this, you would use the product rule. You'd say, oh, there's a product right here between, right? Here, the argument of the tangent function is the actual sine function. So the sine function is getting plugged into the tangent. Okay? All right. Let's see if we can't go around the classroom. We'll take volunteers first. Once you've answered today, you can't answer again until we've gone through everyone. Okay? So who wants to give me the first piece, the first part of this derivative? Go ahead. Secant squared. Say again, secant squared.
And then you keep the sine x.
Sine x, so secant squared. Just tell me either what to write or say it.
Secant squared
Parentheses, sine x, close parentheses. Or you could say secant squared of sine x, right? Just don't say secant squared times sine x. That doesn't make any sense. It's secant squared of sine x. So what do we do here? We ignored this inside, right? Like, let's just say that's my hand, okay? What's the derivative of tangent of my hand? Secant squared of my hand, right? That's because derivative tangent is secant squared. Now I write multiplication times, and then who wants the next piece? Go ahead.
It's going to be
Cosine x. And that is the derivative of what was in here. And that's it. That's your answer. That makes sense? No questions? Okay, so it's a single factor, right? It's a single thing. If I had a plus or a minus here, then I would need to put parentheses. Let me give you one like that. Okay, how about this? How about f of x equals, let's go with cosine. Cosine, and then inside let me do tangent x plus x squared. How about that? And while you think about that, I'm going to graph it just because I want you to see just how cool these functions, I'll call on you a second. Hold on. I want you to see how cool these functions are in terms of, like, we can really start to open up the possibility of, functions and what we're able to find slopes of tangent lines of. Right? Remember, the derivative gives you the slope of the tangent line. So what we're doing is we're seeing, like, even a very complicated function, we can still find slopes of tangent lines so long as we can calculate this derivative. That's a weird looking function, huh? Okay. Was that a question, or you want to answer the first part?
I have a question.
What's the question?
So on the last one, I kind of had some confusion because I understand why and you replaced tangent with secant
Derivative of that's this, and then you bring the argument with you.
Yeah.
Okay?
The only thing I don't get is when we took the derivative of the argument, why we didn't replace it. Because that's what kind of makes sense. to
Why
me,
we
like
didn't
how
replace.
Like kind of how we replaced tangent and secant squared. I would think we replaced sine x with cosine x.
Okay, yes, I understand what you're saying. You're trying, so with the chain rule, you have to go one layer at a time. So you differentiate the outer layer, and then you evaluate that at the inner layer not differentiated. Okay, so this is my inner layer, this is my outer layer, right? I take derivative of the outer layer, and into that outer layer, I plug the inner layer without taking its derivative. Then I multiply by the derivative of the inner layer. That's the chain rule, okay? I know that naturally you want to just do them both at the same time, right? Like derivative of that secant squared, derivative of that's cosine, and then be done. But that's not what the chain rule says you do,
Okay.
all right?
You have to bring it out.
You have to.
And you said like you could bring it to the front if you wanted, but also you could leave it like this.
Yes, you mean this right here?
Yeah. So this
Yeah,
is
you can
fine.
leave it there, or you can move it out to the front. Just don't put it in here, because this is trapped inside the secant. Yeah. So like the biggest mistake I see for students starting off is they do exactly that. Like for this, they would say, oh, derivative of cosine is negative sine. And then inside of it, they put what? Secant squared plus 2x. That's wrong. You have to first start with the outer layer, differentiate it, don't touch the inside, and then multiply by the derivative of the inside. All right, so here the derivative would be, so starting with the outer layer, derivative of cosine is negative sine. Oh, I'm supposed to ask somebody, but I'll get you on the next one. And then inside, I do not touch, right? I do not touch that. That's my inner layer. Then I say times, and now I'll take a volunteer. Go ahead.
Secant squared
Secant squared
x plus 2.
x plus 2x, and do I need parentheses?
Yes.
Yes, I have two terms, right? There's a plus here, so I must put this in parentheses. And that's your derivative. Yes?
Oh, do you need a power rule for x rule?
Pardon me? Yes, Yeah, because once the chain rule, there's no new rule, like power rule's still there, product rule's still there, everything's still there, right? It's just now we have this additional, like, composition. How do we deal with it? I've avoided all problems you've done up to this point. I've avoided composition. I have not done anything that has a function plugged into a function. It's always either been x to a power, or it's been a product rule of things that are like x's to powers or trig functions, but nothing like this yet till today. How about this? You're not going to like this. I feel like y'all are kind of getting this, so I'm going to see if I can push a little bit. Take a moment to look at it. Do we have composition here? Do we have a function inside of another function? Yes? Okay, what would the inner layer be? What's the inner layer of this? X sine x. That is being plugged into the sine function, right? So we have composition, which means we're going to need the chain rule. So we need to start with the outer layer, take its derivative, don't touch the inner layer, then multiply that times the derivative of the inner layer, right? Okay, who wants to start us out with the first part of this? Let's see, go ahead. Cosine of x sine x. Said perfectly. That's exactly the way you say that. Cosine of x sine x. All right. Times, okay. You see what's going on? You got your hand up. Do you see what's going on? Can you explain to everyone what's happening on the inside? Because you have to take derivative of this now, right? Yeah. So what are you going to have to use? What do you see? What do you see right here? Multiplication, which means you're going to have to use the product rule from last class, right? You have to see, this is a product, and you need to differentiate that, don't you? So you have to use a product rule. See, we know that this right here is just the derivative of what was in there. But if what was in there is a product, then you have to use a product rule, right? You want to go then? Yeah. Okay. So I'm going to help you by at least putting a parentheses, because we know that this is going to be a bunch of crap, right? Because the product rule from last class. Let me put the product rule here for us again. That's your product rule. This is your quotient rule, which was essentially the product rule with a subtraction and then dividing by the bottom square. This is a slightly different notation than I used last class. I'm not putting the x's. I'm just saying if you have f times g, so f prime g plus g prime f. I think you get the idea, yes? Okay, go ahead.
1 times sine x plus cosine x times x.
Perfect. There you go. That's it. So what's happening here is we have a product. See, we're ignoring this. We already took care of this. That was the cosine of x sine x. That's done. So we just had to differentiate that. So we say this is like the f and the g. So derivative of this, 1 times this, plus derivative of this times that. Boom. Done. Done with the product rule. And we are done with the problem. We could clean up a little bit. We could get rid of the 1. Like 1 times sine is sine, right? Questions here? How are y'all feeling about this? It's okay so far? Yeah? Let's try another one. This is the raw derivative, right? I'm not doing any sort of cleaning up of this. How about this one? X cubed sine of 3x. Who wants to volunteer kind of the starting point of this one? Everyone's like, no. Okay, go ahead. Can you tell me what you see? Because that's an important thing for everyone. It's a product rule. Everyone see that there's multiplication. Right here, yes? All right, so we have multiplication here. Right here. Okay, I'll let you continue. Is it all right if I go a little slower? You're doing the product rule right now, right?
Yes.
Okay, so
I'll take the derivative of the first one.
Derivative of the first one.
Sine 3x.
Times the second one, sine 3x. Plus.
Cosine.
It's all right. So hold on. You're going to take the derivative of this one now, right?
Yes.
So let me write that down. Sine of 3x. You're going to take its derivative next, right? And then, any more?
And then x
Cubed. Okay, everyone see that is the product rule written down. Without taking any derivatives, that's just what the product rule says to do. I have two things being multiplied together. I have to notice that it's multiplication. And then once I do that, I just write down the product rule like last class. Now let's actually take these derivatives. So derivative of x cubed, 3x squared,